Hello everyone, welcome back to the channel. In this video, I'm going to show you how I made this RBD simulation in Houdini. Before we dive in, make sure you are familiar with Houdini basics like nodes, SOPs and simple simulations. So let's jump right into it and break some cubes.
Okay, so let's first start by observing this simulation. So if you observe this, one piece is being break to 8 pieces, then among the available pieces, some of them break further and then this process repeats. So this is how the animation is going on. Now one thing to notice here is that the pieces have collision in between them and also they are colliding with the ground. But while colliding, they remain rigid, they doesn't get deformed. So this gives us idea that this is a kind of rigid body simulation. So now we have one conclusion that this is an RBD sim. The second thing which we can derive is that there is a recursive factoring which is going on during the simulation. Okay, so let's start by doing the basic setup for our RBD simulation. So for that, we open Houdini and then let's create a geometry node. And inside geometry, let's name it as cube sim. Inside this, drop a cube. Let's move this cube upwards by using transform node. And now for doing RBD simulations, we can use RBD Bulletsolver node. So I will drop RBD Bulletsolver node. And this is our main solver which does all the simulation thing. So if I play, you see the box fall down. So currently there is no ground. Let's activate the ground. So in RBD simulation, under collisions, you can select ground type as ground pin. And then we have a ground. So now we have the basic simulation. And the next thing is there is a recursive factoring which is going on. So instead of focusing on recursive factoring, let's focus on the single level factor, the base one. So basically there is one cube which is breaked into 8 small cube pieces. So this is which is happening in ground level. So how we can replicate it? Now it is very clear that there is some kind of fracturing which is going on. So for fracturing, we can use Voronoi fracture. So inside Houdini, let's make one more box. Let's drop a Voronoi fracture node. So the Voronoi fracture takes 2 inputs. First is the geometry which we need to fracture, and second is the point. And these points are the reference point according to which this Voronoi fracture will run its fracturing logic. Now for geometry, I will input box as the geometry, and for our points, I will scatter some points inside the box. So I can drop a scatter node, put this input as a box, and then inside scatter, currently the count of scatter point is 1000. Let's reduce it to 8 because we want 8 equal pieces. And then we can pass to Voronoi fracture. And then we can see our geometry has been fractured. And to view this, we can use Extro. Now we have a geometry which has been fractured. But one thing we can observe is that all the fractured pieces are of random size. We don't want this. We want all our fractured pieces to be of the same size. So how we can get that? Now the way Voronoi fracture works is, suppose there is a cube and I want to break this cube into 2 equal pieces. Now how can I do this? Suppose I want to break this cube into 2 equal pieces like this. Then I want a point which will be in the midway between this half, and one more point which will be in the midway between this half. And this will break the cube into 2 halves. Suppose I want to break it in 4 halves. Then for that, I can again have point at this positions of the cube. Now similarly, if I want to break this cube into 8 equal pieces, then for that I want my fracturing point to be exactly at the center of the diagonal, at the center of the semi-diagonal. So suppose this is the centroid of the cube and this is any corner point, let's say A, then I want point which is exactly in the midway between this AC vector. So let's say the point B. So the length of BC will be equal to that of BA because point B is in midway between this diagonal. Similarly, each of the semi-diagonal will have this point. And if we have this points and we pass it to the Voronoi fracture, then we will get 8 equal pieces. Now the question is, how we gonna get this point? Well, since B is midway between A and C, we can say that the position of B will be the position of A plus the position of C divided by 2. That means it will be average between these 2 position vector, right? So the B vector will be A vector plus C vector divided by 2. So for that, we need C vector and A vector first. So how are we gonna get that? So let's first focus on C vector, which is the centroid of the cube. Now in Houdini, let's delete the scatter node. As of now, let's disconnect the connection. So let's focus on our box. We have our box, right? We want the centroid of the box. Now, how can we get the centroid of the box? So we can drop an attribute triangle node for that. You can do the same thing using attribute warps, but here doing it using attribute triangle is much more simpler and much more quicker. So I am using attribute triangle, but I will show you the same thing which I am doing here using attribute warp, just to give a hint like how can you replicate it. So now we dropped attribute triangle node. Now what expression do we write to get the centroid? Now what we can do is, since it's a cube, we can use a bounding box. So the bounding box of this cube will be having same shape as that of the cube. So basically the center of the bounding box will be the centroid of the bounding box. And in Vex there is a function named as getBoundingBoxCenter which returns the center of the bounding box. So what we can say is, let's say a vector centroid position. Since it's a vector, we can initiate a variable named as centroid position, and that will be a bounding box center. So how are we gonna get the bounding box center? Now there is a function named as getBoundingBoxCenter. So we can say get b bounding box center. So this is the function bboxCenter, and what this function takes an input is the geometry for which we want the center. So the geometry for which we want the center of the bounding box is the first geometry, right? Because it's the first input, and since the indexing starts from 0, this will be 0th index. So when I pass this, so we have our centroid position. Now to display this, since this is not a global variable, I will try printing it. So I can use printf. And here we can see we have the centroid position as 0, 0, 0. So of course this centroid position of this cube will be the origin of the whole scene. Now we have the centroid position of the cube, which is vector C. Now we need vector A. So how are we gonna get the vector A? So vector A is basically the corner point of the cube. Now one thing to observe is that the neighbor count of the corner point of the cube is always 3. So you see, if you consider this point have 3 connected neighbors, right? This point is one of the connected neighbor, this point is one of the connected neighbor, and this point is one of the connected neighbor. And this is true for each and every corner point of the cube. So we just have to check if the neighbor count of the point is 3, and if it is 3, that means it's a corner point, right? So how we can do this? Now since it is run over each and every point, instead of passing the index, we can simply pass @pt9, and this will run over each and every point of the cube. Now we can write if, and we want a neighbor count, right? So for neighbor count, there is a function named as nig neighbor count, and this function takes 2 input. First one is the geometry for which we are calculating, and second one is the point number. So the geometry is the first input, right? So that will be 0th index, and the point for which we want the neighbor count, and that will be pt9. So this will be calculated for each and every point, and we say that if the neighbor count is 3, then we are going to calculate this thing. So this A will be basically the position of that point, right? So we can say vector A will be the point position. Great, so we got vector A, we have centroid position, we got vector A. So the vector B, which is our center, will be basically A plus centroid position divided by 2. So we have vector B, which is A plus centroid position divided by 2. So now what? Now we have the position of the point, but the point isn't added yet. So we can add it using add point function. So we can say add point. This function will add the point, and for this it takes 2 input. The first one is the geo handle, and the second one is the position at which I want to add the point. So the geo handle will be 0, and the position will be vector B. And now on running this, if we go to wireframe mode, we can see the points are added exactly at the diagonal center, semi-diagonal center. So great, we have points at the semi-diagonal center. One more thing is that we don't want these points, right? The points that will be responsible for fracturing will be these interior points. These points are of no use, so somehow we have to delete them. Now again, the points which are at the diagonal center, they don't have any neighbor. They have the neighbor count of 0, right? Because they are not connected to any point. They are just point lying over there. So we can say that if the neighbor count is 0, that means we are keeping that point. And if the neighbor count is not 0, just simply delete the point. So we can drop one more attribute triangle mode over here, join this, and for deleting the point, we can say that if the neighbor count, again this function takes 2 input, the geometry and the pt9, and we say if it's not equal to 0, that means we are good to delete the point. So we can say remove point. You can use remove point function, and this function takes 2 input. First one is the point geo handle, and second one is the point number. And on running it, you see we delete rest of the points, and just the points that are needed for fracturing are there. Now we can pass this to our Voronoi fracture. So for our Voronoi fracture, our first input will be the geometry, and the second input will be these points. And now if we visualize using export node, we see we have break the cube into 8 pieces. And there is one more thing we can note, that This thing is completely procedural. So if we transform the cube, then also it will break into 8 equal pieces only. If we rotate it, then also it will be effective. So if I transform this thing, and let's rotate the cube, let's move it up, and if I view this now, still it's effective, right? We can also use Boolean fracture node instead of Voronoi fracture, but for Boolean fracture we have to pass the cutting geometry. And there is one more thing we need to take care of, is that if the geometry is moving from one position to another, then our cutting plane should be moved to that position, and also it should follow the rotation which the current geometry have. Then only it will be able to cut them into 8 equal pieces, otherwise the cutting will be messed up. So that's why instead of using Boolean fracture, I go via Voronoi fracture, and I go via this way. This is much more procedural. It is easy to implement via 2 nodes only. So we can rename this node as of now. We can say this as getting midpoints, deleting rest points. Great. Now we can check if this is working or not. So we can move our cube upwards, and we can just add RBD Bulletsolver node and activate the ground plane. Okay. And on playing simulation, yeah, this is working. One more thing which I like to do before passing the input to the RBD solver is to pack the geometry, because packed geometry is much more lighter in weight, since there is only one point which is representing the whole geometry, and this lighter geometry is easier for RBD solver to handle. So that's why always remember to pack the geometry. So I can use assemble node, I can use pack node also for packing, but I always use assemble node. In the assemble node, I will disable this create name attribute, because the name attribute is already created by Voronoi fracture, and I can simply click create packed primitive. So now we have the packed geometry. So what's the difference? If I show you in wireframe mode, you can see that before packing, each of the cube has its own vertices, but after packing, since there are 8 pieces, all the 8 pieces are just represented by 8 single points. So this whole cube is represented by 1 point, and this whole cube is represented by 1. So each cube is represented by 1 point, and it has 1 primitive. So before packing, we can see that the geometry has 64 points, 48 primitive, 192 vertices. Then after packing, we can see the geometry info, it has only 8 points, 8 primitive, 8 vertices. So it makes the geometry lightweight. Now we can pass it to our RBD solver, and it works the same. Okay, so let's set up our scene according to our final videos. Instead of transform node, I will move this cube on the ground by using a match size node. So I will drop a match size node, and I will plug it over here, and I will justify y to be minimum. So this will be on the ground, and now we have our cube on the ground. And if we display using RBD solver node, yep, it is fractured, but currently nothing is going on. Why is it so? Because there is no kind of force in between the cube which explodes them away from the center. So what I basically mean is that we have this setup. Now to get that explosion kind of effect, we want some kind of force that will push the cube away from the center. So suppose this is the center of the big cube, then we need some kind of force that will push this cube away from the center. Now the question is how we want to get this force. So one thing we can do is we can have an initial velocity for this cube. So whenever the cube breaks, it will have the initial velocity, and due to initial velocity, they will be blown apart from the center. And in Houdini, v is the attribute which is used to denote the velocity of the particular object. So we want this velocity vector. Now one thing we can do is, since this is the center of the whole cube, each cube will also have its own centroid, right? So we can have this as a centroid of this small cube. We can create a vector which is pointing from this to this. That means the centroid to the center of the cube, and this vector we can assign it as our velocity. So what I'm saying is, basically, suppose this is the centered position of the whole cube, and suppose this A is the position of the center of the small cube, then we can have a vector between A and C. So for the vector which is pointing from C to A, that vector will be A minus C. So the vector B which we want will be A minus C, and in this way we can assign this vector B as the velocity. So in Houdini, before using RBD solver, we can again drop an attribute triangle node. Let's rename it as set V, and we want to calculate the velocity vector. For that, first we need the centroid of the whole cube. So for that, again we can have the centroid using bounding box. So vector centroid position will be get bounding box center. Geometry will be first, and now we have the centroid position of the whole cube. Now since this is a packed geometry, so each point will be represented by a point which is at the center of that small cube. So we can use this point position to get the centroid, and we can subtract it from the centroid of the whole cube. So what I'm basically saying is that our velocity vector, which will be our vector b for now, will be equal to the position of the center point of the small cube. So it will be denoted by the position v at the rate p, right, minus the centroid position. And now we get the vector b. So we can assign this to our velocity vector using our attribute v at the rate v. So since it's a vector, velocity is a vector, we have written v in front of it, and then we can set it as b. So now we have the velocity, and in our the geometry spreadsheet also you can see we have the velocity vector. And now if we play the simulation, nothing is going on as of now because this velocity vector doesn't have that much value. We can normalize this thing first. So what normalize does is that it keeps the direction of the vector, but it makes the amplitude as 1. So basically this vector will have an amplitude of 1, but it will maintain the direction. So this vector will be converted to a unit vector. And then I can add a float channel, a float multiplier in front of this. So CHF multi and normalize. So now I have added a float multiplier. So I can multiply this normalized thing with whichever the value I want. So I can multiply it with 2 right now. So if I play now, see, we have that moving effect. So I can increase the velocity, I can make the multiplier as 5, and yeah, we have that exploding kind of effect. One more thing we can do is I can add randomness to this. So for adding randomness, we can add randomness on the basis of point num. The way we can do this is we can create a float value, let's say randomness, and we can use a random function. So random function takes an input and gives a value between 0 and 1. So we now have a random value, let's say r, between 0 and 1, and we can multiply this thing with the velocity vector. But if we multiply our velocity with 0, then it makes that velocity 0. We don't want this much randomness. We want our randomness to be in the range of 0.8 to 1, let's say. So how we can do this? We can remap this whole range to 0.8 and 1, and we can do this using fit function. So what I'm saying is basically I'm taking this randomness value and remapping it in between 0.8 and 1. I can again reassign the new value to this previous randomness variable only, and I can say randomness will be fit function. So the fit function takes 5 inputs. The first one is the value which we want to fit, so that value is randomness. Then we have to pass the minimum value that this randomness will have, that is 0, and the maximum value. And then we have to pass the fit range, in which we have to remap this 0 and 1. So that will be, let's say, between 0.8 to 1. So now this randomness variable will have value between 0.8 and 1, and we can simply multiply our velocity vector with this randomness value. Great. So now we can see our velocity is not same for each and everything. There is some kind of randomness which is being introduced in our velocity. Now we have something like this, but still I am feeling there is something kind of off in this animation. So the thing is, when the particle gets exploded, they don't have only velocity, they also have some kind of spinning going on. So we have to introduce some kind of rotational motion. Basically what I mean is that if this cube is moving along this direction, then there will be some kind of spinning or rotation going on along this direction. So the cube will rotate like this, right? Now the question comes, how we can have this kind of rotational motion? So for that we can introduce angular velocity in our cubes. So we can have angular velocity, and in Houdini, angular velocity is represented by an attribute w. So this is used to represent angular velocity, and if we set the value of w, that means it will automatically pick it as the angular velocity. But before proceeding, let's see how actually this w is assigned and how it works. So to show you, let's go back to the previous example, the previous basic setup that we have done. Let's drop an assemble node over here, and let's pack the geometry first and remove the name attribute thing. Now we have this basic setup. Cool. It doesn't have any kind of velocity, any angular velocity, nothing. It's just simply falling down. Let's add angular velocity along y-axis. So for adding angular velocity, I can again add attribute triangle node, and I can say the angular velocity. So angular velocity is represented by w, and it's a vector. So we say v at the rate w will be 0, I want it along y-axis, 1, 0. Cool. And now we have set angular velocity. Now if we play the simulation, you see there is rotation motion which is introduced in this cube. And if we see the direction vector, so if I go to wireframe mode and I visualize the omega vector, that is w, we see the angular velocity is pointing in the y-axis because we have set in the y-axis. So it is pointing in the y-axis, but it is rotating like this. So what's the logic behind angular velocity? Now the angular velocity follows right hand thumb rule. So basically, if this is the vector in which our angular velocity is pointing, then the direction of rotation will be like this. So basically we follow right hand thumb rule where our thumb points in the direction of the angular velocity. Then the spinning axis, or we can say the rotational axis, will be the direction in which our fingers are turning. So in this case, my finger are bending in anti-clockwise direction. So that's why this will have anti-clockwise rotation. So that's why this cube on plane, we can say it is rotating in an anti-clockwise direction. So that's how the angular velocity works. Now in our example, we want this cube to bend like this. Now how can we make this cube bend like this? For that, we need angular velocity along this direction. So if you use the right hand thumb rule over here, then we can see that the direction is like this. So my fingers are bending in this direction, and this will give that cube this kind of motion. And this direction will be perpendicular to our velocity vector. Suppose this is a velocity vector, then this omega will be in this direction. So somehow we need this vector now. Now how are we gonna get this vector? Well, we have our velocity vector, and this omega is actually perpendicular to our velocity vector. So this gives us a hint that if we do a cross product between this velocity vector and some another vector, then it may result it into this omega vector. Now suppose if we take the cross product of our velocity vector and our y-axis, then we will have vector pointing in this direction. This is because the way cross product work is it follows left hand rule. So suppose this is the velocity vector and this is the y-axis which we are taking cross product with. So cross product of a vector with the b vector will be a c vector. So this thumb denotes the resultant vector of the cross product of both the vectors. So this is our a vector, this is our b vector, and this is our resultant c vector. So we are getting our resultant c vector in this direction. We want it in that direction, right? We want it in this direction. So for that, we can just simply do the cross product with the negative y-axis. So if we take the negative y-axis and we do the cross product of velocity vector with the negative y-axis, then we get this vector, this omega, which is perpendicular to v and is pointing in this direction. And again, if by right hand thumb rule, this will denote the rotation along this side. So let's get back to Houdini and let's drop an attribute triangle node. Okay, let's name it as set w. We can set angular velocity by w attribute, v@w, and this will be the cross product between our velocity vector, which will be v@v, and the y-axis. So y-axis, we will take the negative y-axis, so 0, -1, 0, and this will give the cross product. So we can see the w is being created over here. So I'm visualizing w attribute as of now. So for each cube, it is pointing in this direction. So the rotational axis will be something like this. Okay, cool. So we have our w. Now we can normalize this vector. So again, this will have the magnitude of 1. So we can use normalize. This will give a unit length vector, and we can add a multiplier in front of this. So we can add a channel float. Let's say multi. Okay, do this and add the multiplier. And for randomness, we can copy this randomness thing from here, add it over here, and then multiply our omega with the randomness. And now if I visualize this motion, we see we have that angular velocity. So this is looking much more natural and organic. So great, we have our first level of lecturing. Now let's proceed on the recursive thing. Before moving further, again, I also promised to show you how you can do that bounding box thing using VOPs. So in VOPs, if I do attribute VOP node, if I place it over here, if I dive inside, in VOPs there is a bounding box node. So if I drop the bounding box node, if I click it over here, then this will have two input, the minimum and maximum. And if I take the average of these two input, then it will give the position of the centroid. So I can add this to input simply, and then I can multiply it with the constant. So multiply it with 0.5 because I am halving it. And this output is basically the centroid position. So this vector will be the centroid position. If I display this using bind export, we see we have the position of the centroid for this cube. So that's how we can do this using VOPs. I will proceed with attribute triangle only. Now if you see the simulation, we can observe that the SOP geometry is modified inside the DOP network. So basically what I'm saying is that the geometry is modified while the simulation is going on. The geometry is being breaking while the simulation is going on, right? And this gives a hint that there is something going on inside the DOP network. Now in this context, we are manipulating SOP geometry inside the DOP network. So to manipulate the SOP geometry inside the DOP network, we use a SOP solver node. So we can drop a SOP solver and this node helps to manipulate the geometry. So the way this node works is that there is a DOP geometry which is imported every frame, and every frame this same geometry is being output over here currently. Now whatever the modification we want to do or we want to perform, we will perform in between this network. So what we will do is we will import the DOP geometry, we will then perform some kind of modification on that geometry, and then that geometry will be passed to output. So whatever the simulation that will be going to run on the next frame will be on the modified geometry that we have created. So that's how this SOP solver works. Now instead of using this RBD bullet solver that Houdini have made in the SOP level, I will create my own DOP network, and the reason I am doing this I will explain it at the end of the video. So I can cut this node and I can create my own solver. So I can use a DOP network node to create a DOP network. So first we need an rigid body solver node. So we can add a rigid body solver, add this node, take it as an input. Then we need our packed object. So we can import packed object, RBD packed object, and we can plug it in the first input. And this packed object, the input will be our first context geometry, which will be our first input. Next we want a ground plane and a gravity. So we can add a gravity node, and we can add a ground plane. So we add merge node first, and then a ground plane. Great, so we have something like this, and now if I play this, great, we have our RBD simulation working, but the thing is the cube are not exploding, right? This shows that the force attribute like velocity and angular velocity are not imported. So if you dive inside the DOP network, we can see in RBD pack object, there is an inherit velocity from point velocity option, and if we check it, instead of overriding it with 0, 0, 0, it will inherit the values that we provided. And now if I play the scene, see it's working exactly as it is working with this RBD bullet solver node. So if I dive inside, this RBD bullet solver node also uses the same solver. So if I dive inside and if I go inside this solver node, so the Houdini team also use the same bullet solver which we use to create this node. Okay, now what? Now we drop a SOP solver and we pass it as a pre-solve input to this. Let's dive inside the SOP solver. Now moving further, there is one thing to notice is that we are not fracturing each and every piece again, right? We are just randomly selecting some pieces of the available pieces and then fracturing it, right? So we want some kind of variable which will help us to know which cube we will going to fracture. So let's say that we make an integer variable do fracture, and this do fracture will have two values. So basically on the basis of the value it can have either 1 or 0. And 1 means we are going to fracture that cube, and 0 means we are not going to fracture that cube. And we can assign this do fracture value to each of the cubes. So suppose this cube has 1, this cube has 1, this cube has 1, and rest of the cube have 0 do fracture value. This means we are going to fracture these 3 cubes, and we will let this rest of the cube as it is. So this is how we can randomly assign value to the cube, which will help us categorize whether to fracture it further or not. So inside Houdini, the way we want to do this is using attribute triangle. So let's drop an attribute triangle node, and let's name it as set do fracture. Now the do fracture will be an integer variable. So let's say int do fracture. I will be using this variable outside this attribute triangle also. So I want it to be global. So I can say I can create an attribute instead of an integer local variable. Since it's an integer, I pass I, and I at the rate do fracture will be 0. Let's initialize it with 0. Now what next? I have to select some cubes among them to assign the value of 1 for the do fracture. Now each cube have different point number. So I can use random function which will assign a random value between 0 and 1 to each of the cube on the basis of their point number, and then I can filter out that random value. So to show you what I'm basically saying is that I can create a chance variable. Let's say it is a float. So float chance will be random, and that random will be on the basis of PT number. So we have our float chance, and we can say that if the chance is less than 0.2, that means we are setting the do fracture as well. So the probability of this chance to be less than 0.2 will be around 20%, because the value of chance is between 0 and 1, and it will be randomly assigned on the basis of point number. So we are basically selecting 20% of this thing, not exactly 20%, but we can say a probability, and we are assigning them do fracture value of 1. So if we see our graph spreadsheet and if we search for attribute do fracture, we currently are having 8 pieces, and for some of the pieces it has value 1. So for 3 pieces it has value of 1, and for rest of them it is 0, right? So for every frame we have this thing. Now one more thing we observe is that the fracturing is not occurring every frame, right? We don't want our cube to fracture every frame. There are some specific frame only in which the fracture occurs, and then for some of the frame they remain as it is, the simulation goes on, and then again fracture occurs, right? This is how it is proceeding. So we can say that this do fracture value will be 1 for specific frame only, and for specific frame I can say @frame %24 equal to 0. So what I'm saying here is that if the modulo of the frame, this frame is basically the current frame number, so this frame variable will return the current frame with 24, the modulo of this current frame number with 24 is 0, then only I want to fracture it. So the way modulo operator works is that suppose the current frame is 24 and I am taking its modulo with 24, then the remainder of this operation will be 0. So this remainder is basically the result of the modulo operator. So modulo operator returns the remainder of the division. So similarly, if that frame is 48, then if we take the modulo with 24, then again the remainder will be 0. So that's how we are saying that if the remainder is 0 of the modulo operator, then we fracture it. So this will happen every 24 frame, after every 24 frame. Now every 24 frame, so see for rest of the frame, the do fracture value is 0, and once I go to 24, we see some of them have the value of 1. Then again rest of the frame it is 0, and then when I go to 48, then again some of the cube have the value of 1. Next thing is we can split this input on the basis of do fracture variable. So I can use a split node and I can split this. The variable on the basis of which I want to split is do fracture equal to 1. So I'm basically saying that on the basis of do fracture variable, separate the two inputs. So one who have do fracture value of 1 will be on the left, and for the one who have the value of 0 will be on the right. So I will switch the input. I can invert the selection. So I can have the do fracture 1 to be on the right. So I can name this as do fracture, and I can say this as don't fracture this. Great. So we have split the input into two things. We can merge these two things and we can put it as an output. We can merge it and put it as an output. Cool. So now we have the geometry which we have to fracture. So every 24 frame we will have the geometry which we have to fracture. Now we have to write the logic for fracturing this geometry. So we already did the single level fracturing. We can simply copy this thing and just paste it inside the SOP Solver node. So we can just paste it inside and remove this math size node, and we can put this as an input to this two, and this output will be passed to this thing. Okay, so we have split the input, and for the geometry we have to fracture. We are doing the fracturing thing, and after the fracture we are passing everything to the merge node, and then we are outputting it. Great. But one thing to observe is that the geometry we are passing here is an unpacked one, is not a packed one, and the geometry we are passing to the DOP network, we are packing it using assemble now. So somehow the geometry which we are getting over here inside the SOP solver is a packed one. So we have to unpack it first. So for that we can use an unpack node, and we can drop it over here, and then we have unpacked the geometry. Also in the Voronoi fracture, we are overwriting the piece attribute. So piece attribute plays a very important role in RBD simulation. So the way it works is that, let's say there are two pieces. There is one cube and there is one cube. If the name attribute of this piece is piece_1, and if we assign the same name attribute to this piece also, then what Houdini thinks is that these two pieces are basically the part of same object. So these two pieces combinedly form a one geometry. This is what Houdini will think, and that's why this will mess up the whole simulation. So that's why we have to consider our name attribute every time we do the simulation. So in the Voronoi fracture, what we are doing is we are overwriting the name attribute with a piece prefix. So already we have a piece prefix. So in the geometry spreadsheet, if you see the name attribute, here we have piece 0, 1, 2, 3, 4, 5, 6, 7, right? And what this overwrite will do is that it will overwrite the piece 0, 1, 2, 3 again with the same name 0, 1, 2, 3. So the new piece that are being created also will have the same name, piece 0, 1, 2, 3, right? And this will mess up whole simulation. So to fix this, inside Voronoi fracture, instead of overwriting, we can set it as append, and we can say the piece prefix as underscore. So now on 24th frame, we can see we have piece 3_1 piece 3 and piece 4 underscore 2 and piece 4 underscore 3. So what it is basically doing is, whatever the piece it is getting, so suppose it get piece 0 and that piece 0 is being fractured to multiple pieces, then each piece will have name piece 6 underscore 1, piece 6 underscore 2, like that. And then we can simply pack it. We have unchecked this create name attribute because we don't want this assemble node to override the name attribute that Voronoi fracture is giving. Now I think it should work, right? Let's see. So if I run the simulation, yep, it's working. The recursive fracturing is going on over here. But there is one thing I can notice. The pieces are not breaking equally, right? They are not breaking in equal pieces. They are breaking randomly. So why is it so? What did we do wrong? So let's debug this thing. One thing you observe that the geometry for which we are fracturing is this whole geometry, right? And if we see over here, we are fracturing a single geometry. So the logic is same, but we are doing this operation in this whole pack of geometry. We are not doing this operation individually on individual cubes. So we need a way that somehow we process this whole logic for a single cube at a time. So we can do this using a for loop. So we can drop a for loop for each connected pieces. So what this connectivity node will do is it will assign an attribute name as class, and that class will be assigned on the basis of the connectivity of the two pieces. So if there are two pieces which are not connected to each other, then this will have another class value and this piece will have another class value. This means both the pieces are not connected to each other. So in the geometry spreadsheet, we can see there is a class attribute which is created, and each of the three pieces have different class values. So one has 0 value, one has 1, and one has 2. We can also visualize this using color node. So you can drop a color node and then set the random from attribute and set the attribute to class. And this is a primitive attribute, so we can select class type as primitive, and we see each cube has different color. That means they have different class attribute. Cool. So that's how we are separating it, and then for each of the separated piece, we are performing this for loop. So whatever the logic we want, that will goes inside this for loop. And we can see it is written merge equal to 3. So that means there are 3 pieces for which we are performing this logic, and then we are merging those. So now we will add this thing inside this. So we'll go over here. Okay, to explain what this for loop is doing is, you can see at the end the merge value is 3. That means for loop is running 3 times. Now we can click on the single pass thing and you can see what it is doing for each index. So if I display this thing, you can see for the 0th index it is picking this cube, then for the 1th index it is picking this cube, and for the 3rd index, I mean the 3rd loop of the for loop, it is picking this cube, and then it is picking nothing, right? Because it is processing 3 times. So this is how the for loop is working. So now if I play this simulation, you see it's working exactly as we want. So great, now we have our basic RBD sim ready. Further we can do some kind of fine tuning in this. So if I go to this set do fracture attribute, now this is being fractured every 24 frame, right? But I want this frame to be random. So I can say that, let's say int fracture frame, and I want it to be random. So I can use a random variable, random function, sorry, and I can say it set it as frame. So every frame I will have a random value for this, but this will give again result between 0 and 1. I don't want it. I want the frame to be an integer value, and again it should be in the range of, let's say, 18 to 20. So again I can use a fit function. So the input is 0 and 1, and I will fit it in between 18 and let's say 25. Now this fit function is returning a float value between 18 and 25, but we want a integer value, right? So we can typecast it. So we can say int, and we can just enclose everything inside this int. So we are basically typecasting the float to int. So we are converting that float value to integer value, and then we can simply use this fracture frame variable instead of 24. So there will be a random fracture frame variable which will be assigned every frame, and if the modulo of that value with the frame is 0, that means it will fracture. So now if we see the animation, yeah, so we add some kind of randomness. Great, so we have this fracturing going on. Again, one more thing I can do is, since the simulation is getting heavier and heavier as the fracturing is going on, I can limit this fracture. So I can say that do the fracture only if the frame is less than, let's say, 170. So till 170th frame the fracture will occur, and then the fracture won't occur again. So we have this basic setup, but there is one more problem which we will still face. That is, if you see these smaller pieces over here, and if I turn on the sim, you can see that it is still rotating. I mean, there is this small piece are not getting stopped. So there is no such kind of force which is stopping them, and it keeps on revolving and revolving. So this piece has an angular velocity of 10 along z-axis minus 14 along x-axis. So this is a huge value. Now to explain the thing which is going on over here is there is a concept of density, mass and volume. So we know that the density is mass by volume. So basically mass will be density into volume, and mass governs how the object will behave. So the mass plays one of the important role in RBD simulation. Now what happens is that when the pieces breaks, its volume decreases, right? And since the volume decreases, the mass will also get decreased. But velocity and the angular velocity which we have assigned, it will be assigned same to all the pieces, whether it is small or whether it is big. So the small pieces are getting huge angular velocity. And in the simulation, the resistive force which these small pieces will have will be very less. So since the big pieces have big mass, they have more resistance. And since the small pieces have small mass, that's why the resistive force for the small pieces will be less. And that's why they keep on revolving and the angular velocity doesn't get decreased. So the way we can deal with this problem is that we can set the angular velocity accordingly with respect to the volume of the cube. But to do this, there is too much work. So instead of doing this, I can use concept of damping. So what do I mean by damping? So every frame I will check if the value of omega is greater than, let's say, 1.5. And if it's 1.5, I will multiply omega with 0.8. That means I am losing 20% of the angular velocity. So every frame it will lose 20%. And this is the way we can reduce the angular velocity. So inside Houdini, we can again create an attribute wrangle node for this. And we can point it over here. Let's say damping. Let's name it as damping omega. Inside this attribute wrangle, we can say if the length of, so the length function is used to calculate the magnitude of a vector. So if the length of w is greater than 1.5, so we are saying that if the magnitude of our angular velocity is greater than 1.5, then we damp it. So we are basically multiplying our w with 0.8. And now if we play the simulation, we can see the cubes are coming to rest much more faster because there is a damping thing going on, and you can also observe that these small pieces are also coming to rest. So we are now no more facing the problem which we were facing previously. Now finally we can color this whole thing. So we can go outside DOP network. We can color our base geometry first. So we can drop a color node and let's color it. The class attribute for color will be primitive since it's a packed geometry, and we can give this blue color. And this is our base color. Then inside the DOP network, we can randomly assign color. So while fracturing, after the fracturing is done, on the basis of frame, we can randomly assign. So again, for randomly assigning color, I will use Vex code for this. And then over here, I can say that our color. So color is mentioned by CD attribute. So CD will be random on the basis of frame number. So on the basis of frame, it will be randomly assigned, and we have to run it over primitive because since it is packed, the color will be only applied to the whole primitive. So now if I play this, see, once it fractured, the different color is being assigned. Now let's talk about why I haven't used this bullet solver and constructed everything manually inside this DOP network. So if I copy this SOP solver node which we have constructed, and if I go inside this DOP solver and paste this and put this in a pre-solve node, let's go up, let's take this as an input, and now if I visualize this thing, let's go inside the SOP solver first. So if I play the sim inside the SOP solver, you can see everything is working fine, right? The cubes are breaking, everything is working as expected, as we are getting with our own network. But if I dive back and if I go to the base level, if I reset the simulation and if I play now, see, the geometry isn't breaking. You can see that every frame the geometry is getting messed. This is the point where it should break. Instead of breaking, all the pieces which were going to break gets disappeared. And this is the main reason why I haven't used bullet solver. Even I'm not able to figure out what the heck is going on over here. Maybe there is some kind of parameter which I need to check over here, and then this thing will display. But to be honest, I don't know how to solve this problem. If you guys know how to solve this issue, you can comment it in the comment section. But for now on, since this is not working, we will use this DOP network only. And once the ground is set up, now let's move on to the rendering section, which is LOPS. So we can go to the stage context and set up our LOPS. So I will use Karma XPU for rendering this thing, and I can use scene import node. So import scene. Yep. So I will create two, one for the cube and one for the ground. So for this, I will import my cube scene, and here I will import my ground. And then I can merge this thing. So I will use merge to merge them. Select Karma XPU. I will use Karma XPU for rendering this thing, and then we can drop Karma render node and Also we can add camera, so I can use a merge node over here, add a camera, and we can set up our camera. So if we click and lock this view, and then we can add light. So I will use a merge node, and I will add two lights, two directional light. So after working a bit, I have this rendering setup where I'm importing this cube and ground, and then I'm merging them. I have added two directional lights, then this is our camera, and this is our rendering settings. I am also assigning a material. So the base color will be the CD attribute only, which we have set up. There is one more extra thing which I have did is adding an emissive thing. So inside the network graph, inside the SOP solver, you can see I have also set one emissive attribute. So what I'm doing is I'm setting a float value of emissive attribute to 3. So once it is fractured, on the point of fracturing, I'm setting the emissive attribute to be 3. And then I'm damping it. So I'm saying that if the emissive attribute is greater than 1, then damp it with 0.8. If it is less than 1 and greater than 0.2, damp it with 0.1. Else just set it as 0. So this is how I'm controlling that glowing thing, which you can see when the pieces get exposed. And for the cube, in the LOPS network, I have set one cube material. So over here, basically the base color is the CD attribute only. I'm reading it using USD primvar reader. And similarly for the emissive one, I'm reading the emissive attribute that we have set, and then I'm mapping it for some extra control, and then I'm passing it to the emission. That's how the material thing is going on. So I have done a lot of tweaking over here for getting this results. But the thing is, this is the whole technical thing which is going behind this simulation. So yeah, you can try creating something like this on your own, and whatever you have made following this tutorial, you can tag me on my Instagram handle. If you like this video, you can hit the thumbs up button, and if you want more such video, more such tutorials, you can let me know in the comment section below. And if you appreciate my efforts, please do subscribe to the channel. So yeah, that's it for this video. I hope you enjoyed it. Thank you for watching.